The next thing we wanted to do was the Lorentz group, which I will do. So we have two things to do, either do the Lorentz group or do the realization of these groups on function spaces. So let us do the function spaces first, because that is more that is more directly connected to this relating to angular momentum, and we will find some nice results for Lorentz group, but that is later. Okay. So next we look at function spaces as carrier spaces. So that is the big topic, that so far we considered these finite dimensional representations for finite groups, but when we go to continuous groups, we go to the infinite dimensional representations, but they are still countable. And by extension, most physicists also assume that the uncountable ones also are representations. So we will see. In physics literature only, non-denumerable function spaces. So our favorite delta function actually resides in this non-denumerable limit. Okay, we will see that. And so it is called distribution. So delta function, which you write as delta of x minus x prime, you can think of it as a matrix, x one index, x prime the other index, and you can fold in one function f of x, do an integration which is like the index summing over x, and obtain another vector f of x prime out of it. So and are called distributions. So delta function is a distribution. And this goes from minus infinity to infinity, right? So this is like a summation over x prime. Since everything is in red, to highlight I have to use blue. actually the summation over index x prime, and delta, so delta function is the distribution. So now we go back to this we will see business, what is meant by function space. So let us consider functions over a definite interval. Say 0 to L. These can be thought of as a vector space. These have the structure of a vector space. And we can admit complex valued functions. Or we can do it later, but okay, we admit complex valued functions as well, because we want to write e raised to I, ix, etc. So we accept that although the domain is real values, we take complex valued functions on that. Now what we need to check for it to be a vector space is very simple. If I have vector space properties, is simply that f equal to C1 f of x equal to C1 f1 x plus C2 f2 x. Where x belongs to this closed interval, and there is no problem. So we just symbolically, we can immediately check that all the axioms of vector space are satisfied. We can make this vector space also inner product space. We define f1 comma f2, the inner product, to be integral 0 to L of f1 star f2. So remember, we needed this always. So it is like our statement that v1 v2 it was equal to v1 dagger v2. In this is in matrix language. If you take v2 to be a column vector, then v1 has to be made into row vector, but with Hermitian as a Hermitian conjugate, so complexified as well. So the first term has to be first coefficient to be complexified. Otherwise, we will not have positive definiteness. So we need this form. Now the interesting point is that two things. There is a structure of a dual vector space, which is slightly subtle, but the other thing which is familiar to us is differentiation. So differentiation is a linear operator. However, d by dx is not Hermitian. So, next define Hermitian conjugate for operators V1 comma a V2 equal to a dagger V1 V2. So we can check this simply in matrix language. If I take V1 dagger and act on a V2, where V2 was a column vector, so a V2 is also column vector, but this should be equal to a V1 dagger acting on V2, because V1 dagger a V2 is something like V1I star Aij V2j, and that would be equal to Aj star V1I V2j. The definition of the Hermitian is that it is Aj star. So this is what we call the Hermitian conjugate of, so I don't have to put an equality. We want to see what acts as the Hermitian conjugate of A. Yeah, so I think this is correct. So in any case, that is the definition of the Hermitian operator. So for d by dx, note that integral 0 to L f1 star d by dx f2, we can use integration by parts and say this is f1 star f2 0 to L and minus integral d by dx of f1 star f2. Now, to make this into a vector space, we have to put some periodic boundary conditions or some reasonable conditions. So we can set, if we set periodic boundary conditions on f's, then this will be 0. Then A will be its own Hermitian conjugate, right? So now I realized what I did in a hurry. So firstly, we define Hermitian conjugate, and then next we say an operator is Hermitian if it is equal to its own Hermitian conjugate. So this equality actually already insisted that it is self-Hermitian, self-adjoint. But the definition of adjoint is whatever that produces. So this is Hermitian conjugate is that's right. So this was correct, and what we say is if this is same as A, then it is self-adjoint. For X to be self-adjoint now, we should somehow have this also give the same answer as this. And this happens if we choose if we put I d by dx instead of d by dx, then when we then we can write this as equal to star of I d by dx and still retain this sign on F1. So we can start it also by so this, because it's a total derivative, it is just equal to the endpoint values, and this we set equal to 0 would imply that integral d by dx f1 star f2 is equal to minus integral f1 star d by dx of f2, or so the operator I d by dx acts as a Hermitian operator, provided we put this boundary, we restrict ourselves to functions that have periodic boundary conditions. 0 and L, they have same value. So that is an important condition. Now the point is that this has a also a group theory meaning. The operation d by dx has a group theory meaning, and that is why it is an important operator. Next we show that I d by dx is, so I should put minus I, because in physics momentum is put, I mean Schrodinger chose a sign once, so we have to put this minus here. So we show that, it's a matter of convention, but that is the physics convention. Next we show that minus I d by dx is the generator of the operation of translation. What does this mean? So far we considered the rotation group, which is actually the more complicated things. The simpler actions in physics are just shifting the origin, which is called translation in technical language. And just as we had the infinitesimal generators of rotation group, we might then ask what is the infinitesimal generation of translation group. And we will find that I d by dx works as the generator. So to see this, first consider active translations. and this is where I get lost sometimes, but the signs, plus and minus signs. So let us draw some pictures. So consider translations. Shift of origin, that is the meaning of translation. And again, as we did for the rotations, either you have active rotations where you rotate your vector, or you shift the origin, which is the passive action. Okay. So here, so if you shift origin, this is translation but passive. And shift of the function or shift of the state, quantum mechanical state vector, is active translation. So suppose we have a function f, and which sign do I want in the end? Okay. So suppose this was the 0 and we shifted to a new 0. Zero prime, and this is x-axis. So we say that f of, so I have some new function f tilde of x prime system, okay, where f tilde is, I can draw it in blue, it is the very same curve, but thought of in terms of the x prime system that starts with O prime system. Then f at some value x prime is same, f tilde function at a value x prime is same as the function f at the corresponding value x corresponding to x prime. Okay, this is where it is slightly slippery. But it will, the only damage it will do is change the sign, overall sign. But let me repeat. So we want to say I have some functional form f tilde, which is to be read in terms of the blue coordinate system. This functional form, in terms of its own arguments, its numerical value is same as what the other function has as a function of its argument x, which should correspond to the point x prime. Okay. So the way it is written, the domains of both are same. Okay, because the functional form here is f, its argument is x, but x is in the range of the transformation x to x prime. So we have made a transformation x to x prime, and this is what it is. And the x prime coordinates are such that when I have, so x minus a, where this is a. So when x prime is 0, I should get x equal to plus a. Yeah, so plus a. Correct. We can see it here. The x to x prime transformation is such that when x prime is value is 0, the value of the x coordinate is a. So this is the transformation. So therefore f tilde of x prime is equal to f of x plus a. So this is the operation. This operation could be a symmetry operation, but right now we are not saying it is a symmetry operation for some physical system. But nevertheless, we can see that set of all such operations forms a group. Shift by a1, a2, a3, any real number, right? So if we let the domain be entire real line, we have now switched back from finite intervals to entire real line for the time being. So all the operations x prime equal to x minus a, right? Because if x is equal to we did check that x at x prime equal to 0 is equal to so there is a prime here. This is x prime, right? Correct. That's the confusion. So this is x prime plus a, and this is also x prime plus a. Yeah. So all the operations x prime equal to x minus a. So because x is equal to x prime plus a, x prime is equal to x minus a. All the operations x prime equal to x minus a with a again belonging to R constitute a group where composition is simply the sum of individual shifts. I.e., A1 followed by A2 is, what should we call these things? X double prime equal to x prime plus A1 equal to x plus A2 plus A1 is equal to x plus A2 plus A1. So if we do two successive operations, then the equivalent operation is just A1 plus A2. So this is just ordinary addition on the real numbers and subtraction. So the inverse is shift by minus a. And identity is no shift. So this forms a group, and we want representations of this group on the space of functions. So now we go back to our statement. So to obtain the infinitesimal version, so to determine generators, consider f tilde of x prime equal to f of x prime plus a, but put a delta a symbolically. So that is equal to f of x prime plus df by dx at x prime times delta a plus, so using Taylor's theorem. So it is clear that d by dx is the generator of these shift operators. Shift or translation symmetry. Shift is sometimes reserved for strictly those things that are discrete transformations, but we are going to consider all, we have continuum. So d by dx is clearly the generator, and for convenience in quantum mechanics, to make it Hermitian with respect to that particular inner product, we choose minus I d by dx. With P the generator. And we can see that any finite shift can be obtained as exponentiation, because the exponentiation is nothing but the full Taylor series along with its 1 over n factorials. The exponentiation has the 1 over n factorials. So we write but of course eventually you want it to produce the real values. For the classical wave function, classical functions, the usual functions on the function space while we were using Taylor theorem, we do want d by dx back. So we can just write over here, for the time being we'll just write, for the finite shifts we can write like this, exponentiation of a d by dx. But in quantum mechanics, our complex wave functions, we use this as the generator, and so in complex notation So in complex notation, we note the eigenvalues of P are so eigenvectors. Eigenvectors of P are the e to the I k dot x. And we have to normalize it by something. So put it n for the time being. So the structure of the functions on the real line can work for these free translations, and the corresponding eigenvectors in the sense of functions in the function space will be the functions e to the I k dot x, in order to have that inner product we introduced, f1 star f2. And the generalization to 3 dimensions is kind of trivial. Well, one non-trivial thing is there. So in 3D we have f of x and 3 generators. Px equal to minus id by dx, or pi equal to minus id by dx I equal to 1 to 3, with commutation relation that they all commute. The translations in independent directions all commute. And everything else remains the same. There is a square root 2 pi. So some n times e to the I k dot x, and nothing else much changes. So now we can quickly link these things to what we just did earlier, SO3 and SU2. So the translations was a warm up to see how symmetry operations work on the function spaces. So returning to SO3, we can obtain representations on functions of theta phi as the carrier space. And as everyone knows, so let us start with the Cartesian description. And Lz equal to x py minus y px. So we expect I didn't bring out the importance of the shift operator p as the momentum. But anyway, we are not doing physics right now. So whatever the operator p is, I now claim to you that whatever the translation operator P is to obtain this Taylor series correctly, what we need to do is construct the L's as products of such operations, okay, where yx multiplicatively and P is the shift operator for z and so on, okay. So we expect that Lz will be equal to minus I x d by dy minus y d by dx, etc. And we don't want to enter all the detail here. If you go to spherical polar coordinates, then you obtain the YLM as the eigenfunctions. I'm not writing the operator here. So we have the Laplacian operator, which can be broken up into d square dr square plus. Okay. So we find one over r square times, and let me symbol, well, we know what it is. And this acts as j squared or L squared. And the YLM, which purely from differential equation theory and Sturm-Liouville theory, you will get the Legendre polynomials and e to the im plus minus phi as solutions of this. So this we are not as if proving in any great detail, but what we want to bring out is the fact that as operations which constitute a group, rotations which constitute a group, we saw firstly its abstract, first we derived its matrix algebra, and then we checked that that matrix algebra gives a particular commutation relations for the, so let me write it over here. Thus we connect back to matrix Lie group. Matrix group SO3. So the matrix generators Li allowed representations, and we saw that there were irreps because you cannot escape those M representations. With L squared equal to L into L plus 1. And these exactly correspond to the YLM. Of course, this is useful when the potential in Schrodinger equation is separable into r, theta and phi. So but most, I mean, spherically symmetric potentials will give this. So the YLM we use are essentially representations of the rotation group, and when there is spherical symmetry, it is possible to decompose the answer for the wave function in terms of the eigenvalues of the symmetry operations. That is what the summary is. So that is the connection of group theory to quantum mechanics. These things which were first discovered in the context of just trying to solve Schrodinger equation, eventually we understand them in terms of group theory. So result of rotation symmetry. Even if it is not symmetric, it is at least represented by also applicable to so long as R can be separated from the partial differential equation, because then you will be dealing only with this part of the Laplacian and the solutions will all be in terms of the YLM, which being irreducible representations constitute a vector space. They constitute a basis for representing everything that is in theta and that is function of theta and phi. So that is the use of group theory, that is the group theory view of what we do in quantum mechanics. So I think we can stop with this here.